Something is watching from a hole in the reef floor. Two eyes on stalks, raised just above the rim of the burrow. They do not move together. One swings left and holds, while the other keeps turning, as if it has business elsewhere. Across the surface of each, 3 dark spots slide, and every one of them is aimed at you. They are not pupils. This animal has none. No eye is supposed to work this way. The animal underneath is a mantis shrimp. For 15 years, biologists believed they knew what this eye was for. You have 3 types of cone. It has 12. It must see something like 4 times as many colors as any human who has ever lived. There doesn't seem to be much to think about, and for 15 years, that is roughly what everyone assumed. In 1999, 2 biologists in a Queensland lab went looking into a single eye. Justin Marshall and Kirsten Oberwinkler, working on Neogonodactylus oerstedii, a small Caribbean smasher. Their instrument was an electrode, reading 1 photoreceptor cell at a time. 1 wavelength of light, a recorded response, then the next wavelength, and the next. The count they came back with was one nobody had expected. It earned a line that left the journal and never came back. The most complex visual system known in the animal kingdom. So how do you test what an animal sees when it cannot tell you? What is circularly polarized light, and why can nothing else in the sea read it? And why do these eyes never stop moving? There are more than 450 species of them. They crowd the tropical reefs, most no bigger than a closed fist. The largest reach about 40 centimeters, 16 inches, close to the length of your forearm. And not one of them, despite the name, is a shrimp. They are stomatopods, an order that broke from the other crustaceans hundreds of millions of years ago. The group divides cleanly by weapon. Some are smashers, carrying a heavy club folded beneath the head. Others are spearers, firing a barbed limb straight out of the fold. It is the same appendage, driven down 2 evolutionary roads. Each road brings different prey, and a different way of waiting for it. In a smasher, that club sits under a latch, loaded like a crossbow. A spring in the arm takes the strain, and then the latch lets go. The strike accelerates about as fast as a bullet leaving a barrel. The whole movement is over in 0.003 of a second. Water cannot slip aside fast enough, and it tears open. The gap it leaves is cavitation, a pocket of vacuum in the sea. That pocket collapses an instant later, and the collapse throws off heat and a flash of light. So the prey is struck twice, once by the club and once by the water itself. The blow lands with enough force that captive animals have cracked the walls of their tanks. This is our own individual, dug into the rubble at the foot of a reef. It is not hunting now, only watching. In front of it lies a field of shapes that might be food or might be a threat. The 2 eyes move without pause, each turning alone, and neither one settles. None of that weaponry is worth anything without something to aim it. So what is happening inside that eye? Start with the stalks. Each eye rides on a stalk of its own. The 2 move without reference to each other, one swinging away while the other holds still. One eye can lock onto prey while the other reads the open water behind. Neither waits for the other, and turning almost without pause, the pair together sweeps a full circle. For a burrowing hunter, that circle of water is the whole world it can watch. Now hold on a single eye and look closely at its surface. It is not the even, curved dome that ours is. A dark band runs straight across the middle of it. 6 narrow rows of specialized units, stacked one directly above the next. This strip is the mid-band, and it is where the eye stops resembling any other. Above the band sits an upper hemisphere. Below it, a lower one. Most compound eyes are a single uniform sheet of identical facets, corner to corner. This one is 3 separate instruments packed into a single housing, and all 3 of those regions aim at the same point in space. So one eye takes in a single spot 3 times over. It judges depth entirely on its own. We need 2 eyes and a whole brain to compare them. Those 3 dark spots even have a name: pseudopupils. Each one marks a cluster of facets aimed straight back at whatever is watching. The facets pointing your way soak up the light and send none of it back. Where nothing returns, that patch of the eye reads as pure black. 3 regions trained on one point, so 3 false pupils, one for each. In 1999, Justin Marshall and Johannes Oberwinkler set out to count the rest. Their animal was Neogonodactylus ourstedii, a small Caribbean smasher. Their method was electrophysiology, an electrode laid against a single photoreceptor cell. The electrode reads how that one cell answers to one color of light. Shine a wavelength, record the response, then move on to the next. There is no shortcut. One cell, one wavelength, for months on end. They counted at least 12.
You run on 3 photoreceptor types, and most animals have 3 or 4.
So what are all 12 of them for? Their color range runs from deep ultraviolet all the way to far red. It is a far wider slice of the spectrum than the one we live in. We see a narrow band of light and call it the whole world. Ultraviolet begins just past violet, at the edge where our vision quits. On a reef, that light is not some rare curiosity. It is everywhere. Corals, shells, and living skin throw back ultraviolet we will never see. Bodies we read as plain and gray are patterned all across it. Sunscreen pigments, mating flags, territory marks. Much of it sits up in the ultraviolet. Those patterns are not decoration. They are signals meant to be read. So the reef is holding a conversation we have never once heard. Then comes polarization. Light travels as a wave, and every wave carries a direction it leans in. We move through it blind. A camera filter is the closest we ever come. Behind that filter, glare on water falls away, then floods back as it turns. The mantis shrimp reads that lean in the light directly, with nothing in between. It sees a property of light your own eye has no way to register. One use is hunting the very things we would otherwise miss. A transparent animal hangs nearly invisible in open water, until it bends that polarized light and its outline surfaces. The other use turns inward, one body signaling to another in a private light. Almost nothing else down there can read that message back. In 2008, Sirhui Xiu's lab in Maryland went looking for the edge of that vision. Light does not only lean flat across a single plane. Sometimes the whole wave corkscrews as it travels forward. That spiral can turn one of 2 ways, right-handed or left. Some of the eye's rhabdoms, its light-catching cells, answer to only one of them. A right-handed cell stays dark to left-handed light, and the reverse. These were the only cells known anywhere in the animal kingdom that could do it. Circular polarization is common in the ocean, yet almost nothing is built to notice it. Finding a receptor is one thing. Proving the animal uses it is another. So the researchers set them a simple test. 2 feeders stood side by side, each marked with a different twist of light. Only one of them ever carried food. Get the twist right and a meal followed. Get it wrong and nothing came. Training ran for weeks, with the rewards position shuffled each time. The animals learned the difference and chose the right feeder over and over. The wiring runs all the way through to behavior, not idling in the eye, which leaves one likely purpose, a channel almost entirely their own. One hypothesis is that these signals work like a password no predator holds, a message hidden not by darkness, but by the shape of the light itself. 2 of these animals could flash to each other across open reef, in plain sight, unheard.
So if all of that holds, how rich is that world really?
So the legend spread outward. 12 receptors, the sharpest color vision on Earth. It reached school textbooks, aquarium placards, a comic strip read by millions.
It was a good story, and a good story rarely gets checked.
Somewhere on that road, 12 receptor types became 12 times the color. Nobody published that. It traveled on its own for 15 years, and it seemed obvious enough. More receptors, more color, case closed. But the doubt came from inside the field itself. A honeybee carries only 3 receptor types. With them, it separates shades the mantis shrimp cannot tell apart.
So what were the other 8 receptors even doing?
3 types, or 4, already build an animal a rich world of color. More receptors buys nothing on their own. 12 might mean different, then, rather than better. It seemed backwards to me. Surely more sensors should sharpen a picture, not blur it. Here, the problem sharpens.
You can measure a cell, but you cannot measure a perception.
Electrophysiology reads the wire, never the picture. It shows a receptor answering a wavelength and nothing of what the animal sees. The number gave us the hardware, never the experience. For 15 years, the eye had been read, and the mind had been guessed. So how do you test what an animal sees when it cannot tell you? You make it choose. 2 thin optical fibers run into the tank, each carrying 1 wavelength of light. One color means food, the other means nothing at all. The animal learns to strike at the one that pays. Training runs for weeks before a single measurement is taken. At first, the 2 wavelengths sit far apart, and it chooses easily. Then the gap between them begins to close. 50 nanometers, 25, 12. The position is randomized, so it cannot win by learning aside. 10 wavelength pairs, hundreds of trials, 1 animal at a time. And both of the people running these trials had built the legend themselves. Marshall counted the 12 receptor classes back in 1999. Chu found the circularly polarized vision in 2008. They are testing their own legend, and at some point, the animal stops choosing correctly. For weeks, the gap between the 2 wavelengths had been narrowing, and the width where the animal finally lost the thread is the answer to all of it. You can tell 2 colors apart at 1 to 5 nanometers. 1 to 5 nanometers, roughly the width of a few dozen atoms lined up. The mantis shrimp needs that gap to open to 12, and sometimes as wide as 25. A honeybee, running only 3 receptor types, separates shades that this animal blurs into 1. The trouble was never in the 12 receptors, which are real and were counted correctly in 1999. The failure sits 1 step downstream, in a comparison the brain never makes. In your eye, 3 signals are subtracted and weighed against each other. That weighing is where the millions of shades you see actually come from. The mantis shrimp does none of that arithmetic, and its 12 channels never meet. Each one fires or stays quiet, and nothing downstream ever asks the others what they saw. So it does not compare color at all. It scans it. The eye sweeps across a surface, and the receptors fire in turn as it passes. The order in which they fire is the reading, not any comparison between them. The closest instrument we have ever built is the barcode scanner at a supermarket till. It reads a stripe, not a blend, and it reads it in a single pass. And that is why the eyes never stop. What we saw in the first second of this film is the mechanism itself. The eye has to move, because it reads the world 1 strip at a time. This is not a worse eye than yours, only a different one. Its answer arrives at once, with no arithmetic to wait on. No brain here is budgeted to weigh 12 channels against each other. It trades subtlety for speed, reading a color the way you read a name. Fast, certain, and finished before your eye would have completed the sum. Consider what the world becomes for an eye that reads it 1 narrow strip at a time. A whole scene would not arrive at once for it, the way yours does now. It would build across an object in passes, 1 row of receptors answering after the next. And color, in that world, may be a name more than a shade. Not slightly greener than the last thing seen, but the same green met once before. So the eye keeps moving, because a single strip only means something in sequence. Each pass adds to the one before, the way letters gather into a word. Sweep after sweep, until the object settles into something the animal already knows. It seems closer to reading a word than to looking at a color. Away from the electrodes and the feeders, the animal is doing something far quieter. In some species, a single burrow will hold a pair of them for years. They hunt in turn, one out across the substrate, the other holding the door. The one at home guards the entrance while its partner works the open rubble. An animal with a strike like a bullet, and it keeps a house. The pair trade places as the caustic light shifts across the reef floor. Each returns to the same doorway, the same patch of ground, season after season. A settled life, built around a hole no wider than a thumb. But the ground it settles into was never guaranteed. Odontodactylus ciliarus digs its tunnel into that loose rubble at the base of a reef. That rubble was once coral, and coral is what a warming ocean bleaches first. Bleached coral breaks down, across years, into fine sand, and sand will not hold a tunnel open. Nobody has counted what that slow change has cost them.
Turn back, though, to the mistake at the center of all this.
The data itself was never wrong. The 12 receptor classes are real, and they were counted correctly the first time. The error sat one step later, in what that count was taken to mean. We saw 12 where we have 3, and read it as our own eyes, only better. We measured another way of seeing with our own ruler. The correction came from the same names on the original discovery. For 15 years, Justin Marshall was the man who found the best color vision on Earth. In 2014, he signed his name to the paper that took that title away.
This is not failure, it is science doing what a legend never can.
We are back where we started, a hole in the reef floor, and something watching from inside it. 2 eyes on stalks, raised just above the rim. One swings left and holds. The other keeps turning, as if it has business elsewhere. 3 dark spots slide across each surface, and every one of them is still aimed at you. Nothing here has changed since the first second of the film, only what we understand it to be doing. The eye never settles, because it reads the world in sequence. Color arriving as an order, not blended into a single shade. A small animal at the mouth of its burrow, watching in a way we still cannot follow.
Every time we measure another mind, we end up measuring it against our own.
That is how 12 receptors became a promise of color no one could keep.
We know how this eye works, down to the answer of a single cell.
What we cannot do is climb inside it and look out.
So we are left with the honest question, what is it like to see that way?
Has any of this changed what you think seeing better even means?
Answer in the comments and subscribe to watch the next one.